like to introduce Antoine Marot from RTE, which is a French grid network. And he works at the R&D of RTE. And Antoine will present things about system control room operators with artificial intelligence. So thank you, Antoine, for coming.
Thank you, Yannick and Pierre, with some layout. For the invitation. I'm glad to be here. I didn't know Cambridge before, so it's time for me to explore. And so yeah, I will talk about how we're trying to use artificial intelligence to help our operators, to assist them, not to replace them. And so we're doing some collaboration with INRIA, which is a famous research lab in France for AI. And it's a project I've been doing, working on this project for 4 years, so it's a world team, obviously. So we have some stuff to discuss. And along my presentation, I will have some little quizzes for you, like this. This one should not be too difficult. But yeah, let's take some historical perspective and set the stage. So, according to you, how would you rank those achievements for the 20th century?
American Association of Advancement of Science, whatever, said that the electrical power system is the largest machine ever built. Yeah. Which is probably you are aiming at.
That's what they will say.
But internet is closed, right?
Yeah, but it was a bit late in the 20th
I think
century.
internet beat it by now.
But it would
To
not
get your word.
Yeah, it is closer, but it's always a causality.
So yeah, you were right. They did this survey and they had a debate to distinguish which field had the greatest impact in the society. And so the internet, yeah, it's a great invention. It was in the 90s, so it was a bit late to be distinguished. Then television, obviously we all have a television, but then the impact was mostly social. It didn't really reach the industries and change a lot the economy, except for advertising, I guess. And then you had the automobile, for sure. It's gave us a lot of freedom. And finally, electrification. So I guess you could argue between those if one deserves more than another. But for sure, electrification was really a great invention and really changed our societies. And now, so during the 20th century, I guess power systems were a great inspiration for many developments. And so now we're speaking of artificial intelligence. And so there is this researcher, Andrew Rank, so he's kind of famous in the field. He's a Stanford professor who has been working for many companies. And so he has this quote, this phrase, saying that artificial intelligence is a new electricity. So somehow working in this field of power systems, we be kind of proud, but also we can feel a bit old. And why is it saying that? Because electrification really permeated the whole society. It impacted every layers of society and industries. And maybe it's kind of a link, between many things. Maybe artificial intelligence will have kind of this horizontal impact over things. So yeah, you said it, we can still maybe say power system are yet the most complex artificial systems still currently running, but that might change in the future. Let's see. And so, what about power system? Is it so 20th century? Are we done? Are there anything to do still? And so the biggest question is, are we robust to those blackouts? Those are really bad events we fear. So that's the big question. Are blackouts a story of the past? Is everything solved to handle them? And I have another quiz for you. So I'm working at RTE, so we're the French TSOs, and so we're exploiting operating the system. And so we have some operators doing that. But the question is, if we didn't have any human operators intervening on the grid for some time, how much time the grid will be running?
Several minutes.
Several minutes.
But it's in the minute range, yeah.
1 minute range. Yeah, you're right. But I mean, on average, it could be a few hours.
If nothing happens.
Yeah.
Not even a few hours.
It's no
because you have load variation.
Yeah.
Several minutes. Trust me.
So we run some counterfactual experiments, like freezing the operator actions. And yeah, mostly it's about an hour, but as soon as you have big changes over the load curve or stuff like that, it could be in a minute or less. And so yeah, we have still a lot of operators doing their job. So it's far from being fully automated. The smart grid era is still not really there.
It's not that crowded, I
I know, I guess if you look at the number of people, maybe not, but if you look at the number of screens for one operator, then that's what I mean.
Okay.
It's actually, there are other businesses where this happened, like this company of Peter Thiel, Palantir. There's a computer and it's a human, and they have to work effectively together.
Crazy. They're superhuman. I don't know how they work. And so, why is that? That because the system, the complexity of the system has been rising a lot, and we've been adding a lot more applications and simulators and forecasting apps to those operators. And the easy way was to add one more screen with a new application. I think we're reaching maybe some saturation here. And so why the complexity is rising? I think you're all familiar with that. First, because it's a system, and so we have many more actors with a lot more variability at many different scales, so from prosumers to the European grid with a lot more interconnections now. So yeah, it's bringing a lot of new dynamics we have to handle. And also for us, the nature of the grid is changing. We're seeing some revival of DC current. So really AC plus DC brings some new controls, needs, and behaviors. Also, we're not able to build new lines anymore. It's kind of over. We have a flat consumption growth. And also we have a lot of opposition from organizations, ONGs, and stuff like that. So it's not possible to add some more hardware today, such as new lines. So we will push some more software. You're aware that we're getting digital now, so we need to have some new processes to handle that. And also, we'll have a lot more automations all over the grid, which we'll have to coordinate, and we'll also have to manage them. So, yeah, the complexity is there, and it's rising. So, I guess we are not over with blackouts, and maybe AI could give us a little help here. But as you saw, we have quite a crowded working environment. Maybe first the first thing to do is to help our operators and to rethink this control room environment and those human-machine interfaces. So that was the whole idea of the project. Go from multi-screen, so it's about a dozen of screens, to only one single screen, which will display everything needed and everything running in the background. So, yeah, I mean, you can think of this movie, Minority Report. I think you've seen it, and they have some very fancy interfaces. You could think of that, but maybe it's not our first need here. So we will not develop some new interfaces with pen gestures there. It's really a question of strategic information management for us. So what to display to the operator to help him doing his tasks. And so that's what we have today. It's more a supervision mode. with many screens and many applications. And it's a very bad signal to noise ratio for our operators, because as soon as they see an alarm somewhere in a screen, they have to figure out, oh, but is it risky or not? Is it dangerous? What is the context? What do I have to understand? What are the other related information to help me make a study and stuff? So it's really a lot of cognitive efforts for them to figure out what's going on and then start the study. So really what we want to do is to focus them on their task and try to synthesize the information they need so that they can really directly focus on their study. And so rather than having many screens, we'll have only one interface, single interface on the front. It will look like kind of this. I mean, it looks like it. So the most important thing is the feed. So it's, I mean, you're familiar with those new applications like LinkedIn and Facebook and stuff like that, where you have a feed of notifications and cards. And we want to prioritize them. So the most important task will be on top, for sure. So if you have a big risk, maybe because of an N-1 somewhere, and you might lose a whole area of consumption, it will be the top, on the top. And it might be not the first one to come, the first event to come, but really the more risky. Then, when you click on the card, you will have some context about, okay, what this is about, maybe some display of a little area focused on your problem over the grid, and maybe also some suggestions on what to do. I mean, we're doing a lot of recurrent things all over again, so maybe we've been doing it maybe in a slightly different context before, but it's still relevant. So with machine learning, we can learn from habits and make those suggestions. So that's the whole goal. And what we want to do then is to switch them from an alarm monitoring mode, really they spend their time monitoring those alarms, to really coming back to their real work, which is task completion. And so then the idea is to switch from a driving mode to a navigation mode, where they really anticipate everything, they kind of pre-configure everything, and then no hands on the wheel in real time. Everything is already pre-configured, and if something changes in the forecast, then there will be an alarm and a new card to let them know. But they don't have to push a button in real time. And so, I mean, some very common sources of inspiration could be personal assistants. I mean, our fast smartphone now are kind of like that, so they help you plan a lot of things in your calendar or in your life, and they make suggestions. And also another inspiration is the autonomous vehicle. So as I said, you don't want the operators to press the button in real time, because there could be many errors, and they have to anticipate the future. So rather than finding their way and piloting in real time, want them to plan their journey, navigate, and coordinate with others. And so, yeah, just a little focus on our biggest problem for our dispatchers. So what they're afraid to are those lines getting overloaded. And as soon as you get an overload over the grid, you have maybe a few minutes sometimes to react, or no minutes at all. And then you disconnect the grid for safety reasons, and then you could have a cascading effect, cascading failure. So you want to avoid that, and you want to help the operator anticipate and assess the risks, make sense of the situation, and then help him speed up his remedial actions. And so he has to deal with the whole time horizon. So usually it's 8 hours of work. And I mean, at every minute or every hour, he has to study kind of a forecast, a snapshot to see if any contingency could lead to a bad configuration. And so here is a little research platform we have. It's actually open source and it will be used for a challenge. I will come back to it. But you can see a grid in action, right? You have the load conception evolving. You have how much the lines are loaded with the quantiles. And so you can see the grid running, and sometimes you have some lines getting disconnected. So here, there is no action taken, right? It's kind of a very lazy agent, we'll say. And at some point, you have a cascading failure, and it's going down. So really, that's around what we're working. And this task is really a problem-solving task. So first, you want to identify the problem, then you want to look for solutions, and then you make a decision. And here is kind of the current operational process. You forecast the loads, you forecast the productions, you create some forecasted snapshots, and then you study some contingencies. And when you study that, you run the simulators, the physical models, and it's kind of time-consuming. Then you figure out which kind of contingencies could be bad. And at this point, you have to look for remedial actions. And so today, it's purely kind of manual. Only operators look for remedial actions. And it's kind of tactic, because they always have to do something in real time, so it's hard for them to make a strategy over time. And as soon as they have some solutions, they will, maybe close to real time, rerun a study with those solutions, and maybe make some trade-off between security and losses and stuff, and quality of electricity, and they will take a decision. And along this whole process, we're using a lot physical models. And they're great for many things. They're very accurate. They're very interpretable. But they're kind of costly. I mean, until today, we're only having some few representative forecasted snapshots we're studying. So those representative hours. Because it was very computationally intensive. And also, as I said, we have a lot of recurrent situations. Lots of things are happening again and again. And it's too bad, because with physical models, we're not learning from the past. We have no memory of the past. So when you're relaunching a lot of computation, you're relaunching it from scratch, even if you have the same exact situation right before. So maybe we could take some advantage. It needs some very granular input data. So let's say you have a forecast over the UK load consumption, then you need to project that at those substations. So I mean, how do you do that? It's a whole process. And it's maybe not always very satisfactory. Also, you cannot really explore a lot in depth the risk, because again, you're running many simulations. What about uncertainties? Those are deterministic. So it's hard to kind of propagate and backpropagate uncertainties you can have with productions and consumptions as inputs. So I mean, you can do stuff, but again, it's computationally intensive.
Just before, you show some quantiles already on your application.
Yeah.
So you already estimate those uncertainties.
Yeah, but I mean, we were running physical models, so it's not anything fancy there. And then you really want also to explore the space of remedial actions tactics. So again, it takes time. So how can we reach a better exploration trade-off in a real-time operation? That's the whole question. And I think what we can do is better capture the reality of our operations and build on top of prior knowledge we put we could capture. And for that, there is a nice thing which is called machine learning, and so that could really help. So I think you're familiar with it. So I mean, until 2000, expert systems were very popular. They were based on logical rules. And I mean, they had some interesting achievements, especially Deep Blue, which beat Kasparov at that time. But it's kind of brittle as well, because, I mean, those rules, they're made by experts. Somehow we have some high-level concepts we are trying to translate into I mean, logical rules, but our concepts are very fuzzy. So at some point, it's always from an expert, and if you give this rule to another expert, it will never be exactly the same for him. And also, you're not learning, so there's no capitalization on what you did in the past. So you're still exploring a lot of scenarios. So it's better than brute force, but still it's a bit brute force. And now, so you've heard, I guess, AlphaGo from DeepMind, so it was really a breakthrough by that time. And with learning and reinforcement, they were really able to solve this game, which has a very huge complexity. And it was impressive. And now they have, so by that time they did it starting with expert imitation. So they had to learn from experts watching their plays. But now they have AlphaZero, which can learn from scratch. So when you see that, you ask yourself, when you work in industry, are we ready for industrial AI applications in an open and complex environment? That's the question. So, I mean, there is a lot of inspiration, so we should try, at least. And so why learning is interesting? Because you let the machine learn its own representation, so you give it some autonomy in the process. You don't rely only on the experts which are building this machine. I mean, of course, there are some tuning for sure, but you're still relying less on experts. You can infer rules from observations, and you can also capture some field constraints. We have a lot of objects on the grid, some breakers that we never use because we know they're in bad shape, but there's no information in the system. So the operators know it, but the machine will never know it. So when we run some OPF, we might suggest them, oh, okay, open this breaker. They will never do it, and they think it's true. If you learn how they manage the grid, you will never see this breaker open. So there could be a reason why it would be interesting, but at least you're trying to imitate them and only suggest some solutions they're used to. So that's the first step for you. And so we think it could be more scalable, modular, and maybe maintainable, even if there is a lot of thinking there. But yet it's less interpretable, and the robustness of those AI systems are still questionable. So there's a lot of work there. A key catalyst was the advent of neural networks. So those are not new models for sure, but they had some very impressive results since 2010. Well, I mean 12. So now there are really some models to look at, and they have a huge capacity to digest information. So they can overfit in some way, but yet you can really have any kind of input to learn from, very diverse, and then learn a mapping to those outputs. So there is some flexibility there. AlphaGo, if you have to decompose how they did their systems, it was mainly a recipe with 3 main ingredients. So as I said first, they were just imitating those experts. But at this point, the machine is just like a parrot. It doesn't know why it's playing. It should, I mean, it doesn't know it should win the game. It just move after move, trying to imitate what should be a good tactic, a good move. But for that, you need some label data, right? So you need to know what kind of things you've been doing. Then they were lucky to have a simulator. So I mean, a Go simulator is not very complex. But so it's good to play and learn for free. And for sure, for power systems, we've been developing a lot of simulators because we cannot really play on the system just for free. But the thing is that you need a fast and accurate set of simulators. And then once you have that, you can build an architecture, a reinforcement learning architecture to learn strategies and improve. At this point, you really need to formalize your objective and model your opponent. You need to generate an environment in which the machine will learn a good behavior, and then let it explore scenarios with its a priori, it's building and revising over and over as soon as it's playing a new game.
Can I ask you something, Antoine?
Mhm.
Because for this last one, let's say you're in a reinforcement learning framework, that means you need to have still a definition of rewards. You know what you need to reward.
Formalize the objective. Yeah, that's a reward.
Yeah, but so as you were saying for the breaker, for instance,
Mhm.
here it might be a bit difficult to I'd say to formalize or to be clear about rewards because there's going to be so many components that makes it is to be seen as a good or bad decision.
Mhm.
And maybe for some of the decisions, let's say an AI would make, since us as experts, we would never have thought of it, for instance, can we actually say we give a reward or not a reward to this kind of decision?
I agree. When you stay with imitation, you're just imitating. So.
Yeah.
But as soon as you go into reinforcement, then you explore more than.
Yeah, and then
What
we
you were
need to
taught
find the
to.
equilibrium between the expert knowledge and the kind of tactics that the AI is fencing.
So that's why we're far from using
Yeah.
reinforcement for now. I mean, our work has mainly focused on those two steps, and now we're starting to explore reinforcement, but in a very controlled environment we designed.
Okay.
So it's really not on real data. It's just to see the potential of those methods for now. And so yeah, we have, as I said, we're doing many things as a TSO, so from pre-development to maintenance to real-time operations, and we have many simulators. So we could maybe apply this framework to many different problems, but at least we're first studying the real-time operations and how relevant it is. It's also the spot where we have the most data. So, but I mean, we could anticipate to generalize such a framework. So, and now if we try to see what we've been doing and decompose, yep.
So concerning the databases, so you have all the operation on the grid for years or something?
Yeah, mainly we are looking at a database of snapshots since 2010, every 5 minutes.
Okay.
But there is a problem because we have a lot of observations, but as I will say, we don't have any labels. We don't know why we did something in the past. So we can see some interventions, but we don't know why they did it. If it was for the quality of electricity, if it was because of safety, security reason, what was maybe the context, the factors that they took into account to make a decision. So,
and do you have something to calculate the cost? You know, it has generated cost, or any, you gain money with that.
That was my point with the reward.
Yeah,
I think
yeah.
it's ill-defined. You don't even know if there was a cost or a benefit.
But at least you know there wasn't any blackout. But,
yeah, so, I mean, you have to define a reward. Maybe it doesn't have to be as explicit as you will have in other frameworks, but yeah, for sure.
Do you
But for now, what we've been doing is trying to learn some suggestions for our operators. So they're still in charge, and they will be in charge for many more years. So for real-time operations, they're still the ones which decides what to do. So that's also the
Do you run scenarios as well on this, and sort of future scenarios which you believe will on those networks? And
I mean, over time frame.
yeah, so different,
I mean, we want to, but so as I will come, we've been first trying to solve kind of how to, on the snapshots, how to handle the snapshots picture. And now with reinforcement and those new experiments, we're looking at the video. But, so now we're thinking of scenarios, but for now. And so here kind of how we, an AI, it's a big system and you cannot, you need a lot of bricks to build such a little brain. And so for sure we're working on data, we're learning from data. We also need some good representation because every data is not informative, it's not information necessary. So what kind of features also to use, to learn, could be interesting, either for performance or for interpretability. Then when you have that, you can start learning, either by imitating the way we operate the grid, or trying to imitate the solvers, simulators, so trying to learn the physical laws somehow. At the end, the system is still growing, evolving, so you want to adapt, you want to be able to explore a bit more than you did in the past. You want to be able to reinforce and update incrementally your knowledge, and you want to transfer. If you have a new line on the grid, you don't want to throw to the garbage your model. You want to update it, so transfer what you learned on the previous system for this new system. And so here were the two steps you saw in AlphaGo previously we've been working on. For this first thesis, so we have 3 PhDs, so one actually just graduated. I was mainly focused on learning some models to imitate our operators and to learn the physical laws. Now we also have a new PhD which was working on the representation side, because I mean deep learning, neural networks are black boxes. Actually, you can go from data to learning with a neural network without any representation to specify. It kind of learns it by itself. But at some point, then it's interacting with an operator. And the operator has to understand how this suggestion has been made, kind of. So you need some language, and you need to give the operators some context and elements to understand why it's suggesting something like that. And as I said, we are starting to explore reinforcement, but in a very focused and controlled environment. So we'll come to that. So here is our team. So we're 3 researchers. Patrick Pensiat-Dissy, I guess many of you know him. And then we have our PhDs. So mostly we're working with INRIA, Isabelle Guillon, which was she co-invented the SVN, so previous to neural networks, SVNs were very popular. And Antoine Marot, so was a student for Pierre, and we followed together his master's thesis, trying to detect events and labels in energy systems. And so now I will come to the illustrations I have for our works. But yeah, when you're trying to kind of bridge some fields that were very different before, so I know Louis and Pierre, you've been working at the interface of machine learning and power systems for years, but mainly in the community of power systems, machine learning is not used a lot. And so it's like exploring a new island, and you have to get some tools for that. So if you have to go to an island, what would you take with you? To survive, at least.
Is the island covered with a jungle or with a swamp?
I don't know.
Do you have internet on the island?
4G. So I guess the first thing is to have a map. If someone has a map, it would be very useful, and you can figure out if you have a jungle or not. So it's useful to locate yourself and to find things of interest. Then a net could be interesting to fish, to kind of grasp the world around you and work with it. Then you might have some time when running shoes are a good thing, so to explore, but also to react or to free quickly. And maybe the most far-fetched would be the bow tie, because you never know, you could have some nice encounters. So it's always better to look nice.
So you don't need to have something to, that's maybe with running shoes to leave, to get the hell out.
Maybe a bow.
You made a statement about the machine learning people in the power system community. I think there's actually quite a lot of people who want to do machine learning, but maybe what the issue is that these people really just look at it as a toolbox where they just rapidly grab the tool, use the tool and put it back in the toolbox and don't really think about about the context and how far you could go with it and so on. So maybe one of the biggest issues is really that, I'll say, people in this power system community really think as engineers, I've been given this problem, I have only 2 months to fix that, I just try something and then I move on to something else. So it's lack of consistency somehow in investigating the...
And also data, I mean, it's not very publicly.
Sure. But so if you did the same study as Steve on the Google, I think that there's really many people who try to do some machine learning with power systems. But it just maybe doesn't have the, and that's one reason why we said we wanted to have this week. I don't think it has the.
It's also a different mindset.
Exactly.
And it's also a bit like the engineers, they often say, well, you said the same, machine learning tools, neural nets, they are black boxes, but in fact they are not. They're just more complicated boxes, but they're not black. We know what's going on in there, but just many people don't understand it, so it's a black box. But in fact
It's black when you look at it in the dark.
Well, if you close your eyes. But yeah, and this is the thing we have to communicate better and to make it also more applicable.
Yeah, it's interpretability is a big question right now.
Yeah, but it's not a black box.
No, you have a lot of tools you can just like
or Hydronomy
and so first, about the map. So what we want to do is to move from those study tools where they have the full picture. They navigate in this picture to make the study, but it's kind of time consuming. And in our cards, we really want them to focus first, have some context. Before they jump to the study tool because they don't have enough information there, we want them to make a nice representation of the grid so that they might not even need to make a study. They might just select the best suggestion they want. So it's important for them to get a representation of the grid. And so we want to switch from this view, very detailed picture with a lot of data. So it's, I mean, as a human, you cannot handle that. So you need to then identify an area. Today they do it by themselves. They define some areas every year. They say, okay, this area with 50 substation is a nice coherent electrical area. So we'll define it. But can we do something similar automatically? And maybe even dynamically. By dynamically, I mean on every new situation, can we learn a new segmentation? Obviously, we might want something kind of stable across time. So if it's totally different, it's not useful. And so that's what we've been doing. We've been learning those segmentation on the snapshots. And it's hierarchical. So you have this first level of segmentation, then second level, then third level. So depending on what you want to do, if you want to get a sense of the situation, you might just want to look at that. If you want to study an overload somewhere, you might want to look at a smaller area. And so how we've been doing that. This was a paper, and then we submitted also at a workshop at MES. So it was a nice workshop, not in the physical world. There were actually 3 papers on power systems. And so how we do that, it's in 2 steps. First, we need to build a new representation of the grid. You don't have enough information there to figure out what is the nature of your flows. It's a superposition of many flows, actually. And you don't see that in this picture. So what we've been doing is trying to get a measure of how flows influence one another. What is the affinity in between flows? It's kind of a recommendation system. When you're getting some suggestions over Netflix or over Amazon's, they know what you buy, they know what other people buy, then they find some affinities and they make some suggestions. And so what we've been running, a good way maybe to find how a flow influences another, is to say, okay, let's intervene on this flow, let's perturbate this flow, set it to 0, so it's like opening a line, and watching what is the flow redispatching. So let's say you open this line, then it will redispatch over the blue arrow, so in this area, basically. And you do the same here, systematically, all over the grid. So you do the same here, and it will redispatch there. So from that, you can build an influence graph. And then, it's a lot of information. So it's not useful in that way. It's only a small grid, and already it's hard to interpret. So what you want to do then is to make a synthesis to cluster this graph. And more than that, you want to find communities in the graph. And for that, you have some algorithm. And this one, I like it very much, actually. So for those who comes from convex optimization, it's not convex optimization, so there's no guarantee you find the global optimum, especially you're creating variables within the optimizations. So it's kind of tricky, but it comes from Shannon. So Shannon told us how to compress information. Let's say you have a variable with 3 states. So let's say the variable is a city, and let's say your states are London, Oxford, and Cambridge. And let's say you're working at Cambridge. You were born at Oxford, but you don't go there very much. And you go for vacation to London. How would you encode this information to communicate it very efficiently? And Shannon said, okay, we'll encode Cambridge with 0 bits, London with 1 bit, and Oxford with the 2 encoding. So depending on how frequent you use this information, it will determine on the encoding you will select. But you can do better than Shannon, actually. You can do it recursively. It's very, if you imagine a map, you are on your island or in a new country, and you're trying to understand this country, you're trying to find out communities, cities. You don't really know where they are, or where are the limits of those cities, but you're trying to make a cartography of your country. And defining communities is very useful because usually when you're a community, you only live mostly in your community. So you don't have to communicate with other people. And so if you look at maps, you have streets, you have cities, and you have areas, regions. You can have the same name for a street in different cities. Why can you do that? Because you can name the cities, you can name the communities. And so it's more efficient not to give a different name to every street, but to give sometimes the same name and to add to that a code book, what they call it, to define an area that you will use when you switch from one community to another. So it's very efficient in terms of information compression. And so when we do that, here is the segmentation we find. So we could see that in our blue influence graph, we could see kind of 2 areas with some density. So that's what it finds. And then we did the same stuff on some grid benchmark. So it's 3 times the same grid, so hopefully we segment those 3 subgrids in the same way. And then we find an interesting other community, which are the interconnected lines. And they're not, it's a community that is not connected in the topology. So somehow, if you were only looking at the topology, you will never find it. But what it's saying is that those lines have really the same behavior for the grid. If we lose one line, then the other line will take over.
This is state dependent, right? Because you were saying it's
state dependent. And here was the last result over France. So that was really striking. So it's qualitative, right? And we didn't specify it's an algorithm. You don't specify the number of clusters of communities. You don't specify the number, the depth, because it's hierarchical. So it kind of finds itself the number of communities and the depth. So it's nice. I mean, you don't have branches that converge, but you can still look at the results. And this result was saying that we found out that the same number of regions than the one we have at RT. So RT is actually segmented into 7 regions where you have control centers for the regions. So I mean, it was made like this because somehow of electrical considerations, but for also other considerations as well. But maybe since then, so in the 90s, since then, the grid was developed mostly in regions and not totally taking into account some national development. So if you believe this is kind of a nice segmentation, then you can have a lot of debate why is it segmented like that. But you also need to validate this method. So we're here still in the process to have some more quantitative elements to validate it. So I will not have time to make the demo, but basically you can segment your grid and then look, zoom into some areas to find out what's in there, what are the characteristics, what is the production, consumption, exchanges with other areas. So it's quite interesting. Then the nets, we'll try to go quickly.
we can go a bit over time. I know it's okay.
Okay, so the net, I guess you will have guessed it's about neural networks. And so we've been trying to complement those physical models because, as I said, they're kind of computationally intensive. So how can we use neural networks to go faster? Maybe not as accurate for sure, but at least faster.
Sarah, could I just interrupt you just to understand the driver? Because the power flows are quite fast at the moment. You can calculate even thousands of nodes power flow pretty fast. So what's the driver from moving to actual mathematical accurate representation to your neural nets, which is approximate?
So it's to run scenarios and to learn with reinforcement. So and it's to really learn over time, over a trajectory of many scenarios. And you want to explore a lot of flexibility, remedial actions. So you have a lot of contingencies and risk to assess. And you have many remedial actions you can run, you could find. So that's why we want to screen the space. And then, as soon as we find some interesting spots, so maybe an interesting remedial action, we'll validate it with a physical model. Will be more accurate.
So this is scenario analysis, basically, multivariate scenario analysis.
Yeah. So
thousands of power flows.
We want to filter. Yeah. We want to filter out everything that is not really interesting.
So you sacrifice accuracy to get time gain, basically.
And so we've been developing two architectures. The first one, so it was actually Benjamin Deneau, who is now a doctor. And it was called the LeapNet. And we have now a new architecture we're looking at. It's the GreenNet. And the first one was really just imitating the simulator, so we'll see. And the second one is almost doing the same thing as the solver. We'll see why. So the load flow, I think you're familiar with it. But you have as inputs injections and the topology of the grid. And usually you compute the voltages and phases. And then you deduce the power flows. And so the first neural nets, so the first try we gave was just to learn over many situations, snapshots, how to predict the flow. So it's very specific to a grid and to a domain of operations. If I learn it for the French grid power system, I will not be able to use it for the German or the UK power grid. So it's very specific, but could still be very interesting.
You mean this network?
Yeah.
But maybe you can.
I mean the method is general, but once you learn a model, you can only use it for.
Can you imagine a network which is general, in fact, because you learn it on different datasets for different network with good covariance? No. It's not.
I mean we have another architecture which is aiming at that. But yeah, it's difficult.
Okay.
Especially it's difficult to integrate the topology of the grid. It's very combinatorial, and it's not easy. So here actually the inputs are production consumptions and some topological variables. So basically if a line is connected or not. And here are the flows.
So how many scenarios, how many configurations have you considered? Because you have many variables. So this is one of the main problems with any artificial intelligence in the neural networks. You have to cover the whole possible solution space.
Not necessarily. They're very good interpolators. So not very good extrapolators.
Exactly. So that's what I'm saying. So you
yeah.
have to make sure that you cover everything.
Yeah.
And
And
then you have complexity.
So we have to think about that. How can we extrapolate at least a bit? And that's why we came with this architecture. Actually. So this is a very standard neural network architecture. And when you have discrete variables such as topology, usually you encode them as a one-hot encoding. So every variable has a 1 or 0 if a line is connected or not. But it's very standard. What we did is rather than having the topology variables as inputs, to have them really intervene in the network. And we wanted to really dedicate some neurons to say, okay, this line now is disconnected. It's an event, it's a rare event. And so what we wanted is to learn, okay, in the reference state, what will be the typical response of the system. And now, let's say we have this line disconnected. How do we learn efficiently this new response? And basically, it's just a modulation of the response you have from your reference states. And usually it's local. You're not influencing every flow. So you can activate a new neuron so that it encodes this residual modulation from your reference state. So you're very efficient at learning how your system behaves in the reference state, reference topology, let's say. And then you're trying to learn some modulations around that by activating some neurons. And then you can do some extrapolation. You can only learn n-1, so if a line is disconnected, so you learn it for every line, and then you can predict n-2 without learning it. So that was a very strong result for Benjamin. So that's interesting, but yet we have thousands of topological variables, so at some point it will have some limits, for sure.
Well, you have another dimension, the loading, and again, the loading can be, you have different loading patterns and different nodes. It's not only topology, it's also the loads.
Yeah, sure, but those are more continuous. I mean, for sure, near the local laws, you might have some very discrete behaviors that will be hard to learn. But the topology is really the big.
I mean, if you use the linear model, then
But we're also working for the transmission, and it's less close to different side and stuff like that.
Sorry, just to push you on that, because basically, an alternative, if you want to do it really quickly, you can use a linear network model and then you solve linear equations and then basically forget about neural nets. You get far better estimation, because linear model gives you pretty good estimation.
Actually, we do a lot better than that. That's what. It's because with linear models, so DC approximation, let's say, you cannot learn the voltages, you cannot learn the phases, and you have something like 5 to 10% error. So that's good for some applications, but we do better than that. We have 2% errors on amperes, so on the currents. And we can learn also voltages without having any information on the reactive power. So you can design some new things with machine learning and neural nets. You don't need the same information to predict some interesting variables.
But with the linear systems, you can also do this jackknife thing, taking one line out and then look how the system behaves. And you can check for many options quite cheaply. And I would agree, if you're just interested in taking all the grid, the single lines, the linear system is very beneficial. But the tricky part is the production part. If you have lots of wind in the system or not, in parallel with an outage there and so on, that becomes the really tricky part.
They're good at learning distributions. So I agree, there are some limits, but I mean, in the results, we showed that it was interesting. It might not be accurate enough for real data in every application, but to rank maybe the most dangerous contingencies, we showed on real data that it was very effective. So it will not work for every application for sure. But in some applications where today you cannot compute n-2, there is no way. I mean, somehow it's not very interesting for every n-2. But we showed that with combining this neural net with some physical model to recompute the dangerous contingencies, we could achieve a very good risk assessment a lot faster. So, I mean, you have to project that into an application then to figure out if it's the best way or not. I mean, we're not saying it's the thing you should use for every.
So is it really that the advantage of the methodology would be with non-linear aspects of power system operation, which are the voltages? Because just for power flows, it's basically a linear model, and you can solve thousands of equations in a split of a
Linear
second.
models, but when you add the topology, it's non-linear. When you at RT, we operate a lot on the topology, and we have a lot of non-linear behaviors. And so then your linearization is good for one topology, or if you disconnect a line or not. But if you split a node, or if you merge a node, then you have to recompute everything, so it's not very efficient. Just this new idea quickly. So in the solvers today, we're using a lot of Newton-Raphson, and basically a Newton-Raphson is it's an iterative solver of nonlinear and linear iterations. And so you could actually think, okay, why not do that in a neural network? Every layer is a linear and nonlinear operation. So you could use a neural network to learn one iteration of your load flow at every layer, and that's what we've been trying, and there's some good results. And to do that, you're also injecting the topology at every layer. So you're giving some information to your neural network about what is the structure of your grid. So you're not saying you're not constraining your network to follow the physical law such as the node, that's right in Kirchhoff plan. Yeah. So you're not imposing your model to follow the Kirchhoff law, but you're saying, okay, here's how the lines are connected, and somehow it will learn it. And so what you want to do actually is to propagate information. You have information at some source nodes or sink nodes, production and loads. And then how will that translate into flows? And so what you want to do is some iteration. So you start with your inputs, the information you have at first, and then you propagate. So first iteration, you might have this result, so it's not very good. You might deduce you have 2 loads and 3 productions, but then it will exchange information all over the grid, and it will converge to, it's supervised, right? So it will converge to the results. And the interesting thing is that you can learn on a small grid, small topology, and then generalize to any grid. So that's what we're trying to aim. Because you're learning how in a neighborhood, so you're trying to look at every kind of neighborhood you could have on a topology, how given some information on the neighbor nodes, you will converge to have an information or a phase on your node here. So really it's a convolution. It's a convolution of a graph. And that's what really helped into image recognition at that time, is that they use convolutions to really take advantage of the symmetry and the recurrent structure of the problem into pictures. So it's a paper that is actually in review at IGCN.
So you need to know the graph or assume a graph? Or?
Yeah, so now you need to know the topology, like your physical solver. So that's some trade-off. Because for the other model, you didn't have to know the topology. Maybe some lines were connected or not, and you could still infer some nice predictions of the flows over specific grid.
Yeah. So I can't still see how you can beat Newton-Raphson with this one if you assume the topology is the same.
But Newton-Raphson, you were talking about accurate methods. You call it Newton-Raphson accurate?
Yeah, well, it's certainly more accurate than
it's only accurate if it works.
A and N are certainly less accurate
So
than Newton-Raphson.
the only goal is not only to beat Newton-Raphson. I mean, we're not aiming at beating Newton-Raphson. We're aiming at having a nice hybridization of models, physical models and machine learning models. But with this, you can propagate maybe uncertainties also. So you can learn a lot more easily uncertainties, and you can do some end-to-end learning. When you have an application, usually it's a succession of brick after bricks after bricks with interfaces. And at every interface, you break some distribution, you break a lot of things. So here you could have a brick that could be relearned in an application. So it could be specialized toward an application. It could be used to learn distribution. So we can anticipate some new applications. But we're not aiming at replacing actually but it's still exploratory. Here we have the same characteristics, same impedance for every line for this first work. So we need to incorporate that for sure. But it was a good way to demonstrate the
Let's try to close within 5 minutes.
okay, so here are the numbers. Here it's about 500 to 1,000 faster computation time than a classical solver for the first implementation. But then it's not able to transfer, to extrapolate to many different grids. So it can be a limitation. And here we might be not as fast, but then we can really extrapolate to many other grids. And that's what I was saying. So you can specialize your model within an application to learn it end to end. and you can propagate and learn uncertainties. Okay, so I will leave you watch those videos. So here we were trying to tackle reinforcement, and there we had a great inspiration at MES 2017. This was a competition where they were trying to work. So they had a physical simulator which was modeling and simulating how you will, how the muscles will react when moving. But it was very difficult to learn to work with the control. There are many parameters, and as soon as you try, you fall. So they designed a reinforcement learning framework to attract the reinforcement learning community on their problem. Those were Stanford researchers, and they had actually very, very nice results. And so we're trying to do the same for the power system, trying to avoid cascading failure, which is the analogy for it. And so that's what they did. They had a simulator. They made an API in Python to interact with the model. They designed a game environment. So it's not free. You have to design the environment in which your agent will learn, and it should be interesting enough and maybe progressive so that the agent learns. And then you run some RL. So again, there is a lot of work there. So here we're trying to attract the RL community with a challenge. So I will not go over that, but we modeled our problem, so it's simplified, right? We cannot design a new synthetic environment with the whole complexity of real-time operations. So we're trying to go step by step. And first, it's to maintain the security of the grid, running some topological actions. So here is our environment. So different productions, loads, could have some maintenance work, and we could have some contingencies. Then here's a space of actions. We're focusing really on topology. Redispatching and load shedding could be used. They're studied a lot in research, but they're costly for us. So we're more interested into the topology part, and it's also a research problem. It's non-linear. It's very hard to handle those topological changes in OPF or stuff like that. So it should be interesting. So if you're interested, just to take a look, it will start in May this year within the IGCNN conference. So you can compete, of course. But it's more the framework is designed around reinforcement learning. So it's based on OpenGym, so OpenAI, it's a company, it's an organization in reinforcement learning. So it's really a format for rather researcher in reinforcement learning. So please join. And finally, just a quick thought about labelization. So ImageNet really was a great, was a great work to bring some new breakthrough into the machine learning field. And suddenly, neural networks proved to be quite interesting when you have a big database of labeled data, which is very, which is not noisy, which is balanced, no missing data, not very heterogeneous. But that's the whole problem we have with industrial databases. And also, as I said, they are not labeled. We see observations, but we don't know what we did, why we did things. So it's really a problem to learn to imitate, for instance. And so so load curve prediction is really a nice sandbox when you're trying some new methods. So that's what we did. We have a whole database of daily load curves. And we're trying to characterize and label them effectively. So how could we develop a method for that? And one good thing usually is to reduce the dimensions. So we had PCA in the past. And so because in high dimensions, every data point is very far far from another. So you cannot really learn a similarity measure in high dimensional space. So, but you can do it better in low dimensional space. And so now there is this new kind of models which are called autoencoders. And they're actually a generalization of PCA. You could learn a PCA with an autoencoder having only linear operations all along the way. They're also variational, so they're learning to generate, and you can give a prior, so like a Gaussian prior, and you could learn some uncertainty in the model or to generate a bunch of scenarios. And you can also condition them. So you can say, okay, now I know I'm in winter and we'll have this temperature profile. So I want to learn a model that is able to take this information into account and only learn the residual, learn to decompose the thermal part from the other part. So with the conditions, you can also learn progressively, you can integrate some expertise. As soon as you have some new labels, you can give it to the model and it will focus on the residual and learning some interesting characteristics. And so that's what we do. We have some load curves, we're projecting them in the encoder part, the latent space, and then implicitly we learn a similarity measure. And we can then explore this database. And then when we explore this database, and we could know that some features could be relevant or not. So for instance, here is weekday. Am I a weekday or not? You can figure out that in the latent space, you recover some known features. And then once you select those features, you can integrate them. So as I say, if you discover that the temperature is very important, you can integrate it into your model. And then the latent space will only learn some characteristics for the non-thermal part of your load curve. So you can figure out that there are other features, other latent features you were not able to see before. And so now, iteratively, an expert can label and build a model. So you can go from unsupervised to supervised model with this kind of methods. So, able to add. So here, if we recap, so the bow tie was for data labelization, mapping was to learn some nice representations, the nets were for no nets, and the shoes were for reinforcement learning, so learning to run. Okay. Yeah, and the idea is really to replace the simulator which was running there by those proxies. So those are approximates, but it's not the time you're taking a decision. So we still validate with the accurate model and physical model before taking a decision. And then you can learn some strategies. You can also design an expert system. We actually have an expert system to have them help us explore the space of remedial actions. But it's all learning in the background, right? So that's why they're grayish. And so what we define as artificial intelligence are those three components. So component for learning, trying to integrate some expertise from our operators and rely on physical models, because without those bricks we couldn't do anything we've done until then. And yet we still have to think that the operator will be there taking decision, and this AI will have to communicate somehow with this operator and to kind of explain what's going on. So at some point we'd like to be a little assistant, so we're not there yet, but that's the idea. And so, yeah, AI can really help us better handle information. So better information processing and continuous learning as the system is changing. We need to design a robust and lasting AI. So today we kind of learn maybe every month a new model, and we throw it away and learn a new one. So it's not very robust, and an operator will not like that because he will not grasp what is going on. So we need to think about that, but not to come back to those expert systems only, which were kind of brittle because you really impose some rules that are kind of fuzzy. So leave the machine some autonomy to learn, but obviously you can inject some expertise in those models. It's very useful. Grow your AI brick by brick and test it in very diverse decision-making environments, and maybe following a curriculum. So that's what we're trying to do, for instance, with reinforcement learning. Doing it in a synthetic and controlled environment, and at some point maybe jumping in some years to the real world. We're not trying to replace physical models and existing solvers. We're trying to find the good trade-off, a good combination, an hybridization of physical models and machine learning models. There is no free lunch. Each one has its own advantages or limitations. To find better trade-offs in computation time, accuracy, or confidence, and uncertainties or trust also for operators. And then there are still many open challenges. Uncertainties, we talked about it for sure. Human-machine collaboration, but also multi-agent cooperation. You might have multi-AIs running in an area, and they will have to coordinate. Or you can think of multi-automaton in the grid. They need to have a sense of what the other one is doing. And also a big challenge is interpretability and causality. Without controlling those models, we'll not be able to manage the system. So really need to know what are the factors that kind of influence our decisions and change the system behavior. And so coming back to this analogy between AI and electricity, I think the only difference is that for one we're talking about energy, and for the other we're talking about information. But those are really two mediums where you can efficiently process and transfer something. And we're aiming at what we call now cyber-physical models of system, because everything is kind of digital. You can have a decision that is taken in East Europe and has a direct impact in the West Europe without the flows being propagated. So it could be very tricky. So you have to think about that. And if you want some references, here's